Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question that is both simple and impossibly deep. Why does the universe seem so perfectly arranged for life to exist? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the nature of reality together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. If you pause for a moment and notice the world around you, something rather subtle begins to reveal itself. Not loudly, not dramatically, but in a quiet, persistent way. Things, work. Your body holds together. The air stays where it should. The ground beneath you doesn't suddenly let go. Light travels in straight lines, stars shine steadily in the distance, and atoms, those tiny building blocks of everything, remain remarkably stable, holding their shape across billions of years. It is so familiar that it almost disappears into the background of your awareness, like the gentle ticking of a clock you stopped noticing long ago, and yet, if you let your thoughts linger here just a little longer, a quiet question begins to form. Why does it work at all? Why do the pieces of reality come together in a way that allows anything to exist, let alone something as intricate as you, lying here, listening, breathing, thinking? You might imagine at first that this is simply how things are, that the universe could not have been any different, that these patterns, these rules, these behaviors are inevitable. But as physicists have slowly uncovered the deeper structure of reality, something unexpected has emerged. The universe does not just follow rules. It follows rules that depend on numbers. Hidden beneath everything you see, beneath stars and oceans, beneath your thoughts and your heartbeat, are a handful of quiet, unchanging values. Numbers that do not shift, do not drift, and do not explain themselves. Numbers that determine how strongly things attract, how quickly light travels, how tightly atoms hold together. If these numbers were even slightly different, the story of the universe would unfold in a completely different way. Not a little different, not subtly altered, but fundamentally, unmistakably, unrecognizable. Imagine for a moment that gravity were just a little stronger, not dramatically so, just enough that the pull between objects increased ever so slightly. Stars might burn faster, living shorter, more violent lives. Planets might struggle to maintain stable orbits. Structures that seemed solid and reliable could begin to collapse under their own weight. Now imagine the opposite. Gravity just a little weaker. Matter drifting apart, unable to gather into stars at all. A universe filled with thin clouds of gas, never igniting, never forming the bright, steady lights that warm galaxies and create the elements needed for life. Or consider the delicate structure of atoms themselves. The way electrons move around a nucleus is not random. It is guided by a balance so precise that even a small shift could prevent atoms from forming stable bonds. Chemistry, the quiet dance that allows molecules to exist, would simply never begin. No water, no carbon chains, no cells, no life. And yet, here you are, in a universe where gravity is not too strong, not too weak, where atoms form easily, where stars shine long enough to forge heavier elements deep in their cores, where, over immense stretches of time, complexity slowly emerges from simplicity. It begins to feel less like coincidence and more like something finely arranged. This idea is often described as the fine-tuning of the universe, not in the sense of intention or design, at least not necessarily, but in the sense that the conditions required for life to exist depend on a very narrow range of possibilities. A slight shift, and everything changes. But there is another way to look at this, one that feels almost paradoxical at first. Perhaps the universe is not perfectly tuned for life. Perhaps we are simply in the kind of universe where life is possible, and that is the only reason we're here to notice it at all. It is a bit like waking up in a room filled with air and wondering why the room was designed for breathing. The answer may not be that the room was made for you, but that you could only ever wake up in a place where breathing is possible. Still, even with this perspective, the question does not disappear, because the deeper we look, the more precise the balance seems to be. Not just in one place, but everywhere. In the strength of forces, in the masses of particles, in the way space itself expands over time, each piece quietly aligned with the others, forming a vast interconnected system that has unfolded over billions of years. And what is perhaps most remarkable is that none of these numbers, none of these constants, can be derived from first principles. Physics can describe how the universe behaves once these values are known, but it cannot yet explain why they have the values they do. They are measured, observed, written into our equations, but their origin remains just out of reach, like a melody whose notes you can hear clearly, but whose composer remains unknown. So tonight, as you rest here between waking and sleep, we will gently explore this idea together, not as a problem to be solved, but as a landscape to wander through. We will move slowly from the smallest building blocks of matter to the vast structure of the cosmos. We will see how simple rules give rise to stars, how stars give rise to elements, and how those elements eventually become something capable of asking questions about its own existence. And along the way, we will return again and again to that quiet mystery. Why does it all seem to fit together so well? Why does the universe allow this fragile, fleeting thing we call life? And is it truly perfect? Or simply one of many possibilities, gently unfolding in the dark? For now, there is no need to answer. Just let the question settle softly in your mind, like a thought drifting across still water. There is plenty of time to explore, and no need to rush. Because in a universe that has been unfolding for nearly 14 billion years, a few quiet moments of curiosity are more than enough. And perhaps, as your thoughts begin to slow and your breathing softens, you may notice something else, that even the act of wondering is part of the story itself. A small, quiet reflection of a universe that somehow has learned to look back at itself and to ask, why? If you gently follow that question a little deeper, something curious begins to happen. The world around you, which once felt rich and full and endlessly complex, starts to simplify. Not in a way that removes its beauty, but in a way that reveals a quiet kind of order beneath it all. You might begin by thinking about yourself, a living, breathing human being filled with thoughts, memories, sensations, a body that heals, adapts, and moves. At first glance, it feels impossibly intricate. Billions of processes happening all at once, each one depending on the others in ways that are almost too complex to fully imagine. But if you slowly peel back the layers, that complexity begins to soften. Beneath the skin, you find tissues. Beneath the tissues, cells. Each cell a tiny world of its own, filled with structures quietly performing their tasks. There are ribosomes assembling proteins, mitochondria producing energy, strands of DNA carrying instructions written in a chemical language. And yet, if you continue to move inward, something surprising happens. The diversity begins to shrink. All those different cells, all those different structures are built from molecules, and those molecules, no matter how complex they appear, are made from a surprisingly small set of building blocks: carbon, oxygen, hydrogen, nitrogen. Just a handful of elements combining in different ways to create everything from your heartbeat to your thoughts. If you drift a little deeper still, even that variety fades, because atoms themselves are not so different from one another. Each one is built from a nucleus made of protons and neutrons, with electrons moving in soft cloud-like patterns around it. And whether you're looking at a grain of sand, a drop of water, or a living cell, the same simple ingredients appear again and again: protons, neutrons, electrons. 3 pieces, rearranged endlessly into different forms, and then, as you go deeper still, the simplicity becomes even more striking. Protons and neutrons are not fundamental either. They are made of even smaller particles called quarks, tiny, almost abstract entities that combine in very specific ways to form the matter we recognize. At this level, the universe begins to feel less like a collection of objects and more like a small set of ingredients being reused in an infinite number of combinations. Like a language with only a few letters, capable of forming an endless number of words. And yet, there is something even more subtle hiding beneath all of this. Because these particles do not simply exist, they interact, they attract, repel, bind together, and sometimes drift apart. And it is these interactions, these quiet relationships between particles, that give rise to everything else. A molecule is not just atoms sitting next to each other, it is atoms holding on to one another in just the right way. A cell is not just molecules, it is a delicate network of interactions, each one timed and balanced with remarkable precision. Even something as simple as a drop of water is not just a collection of particles, but a quiet agreement between them, a balance of attraction and motion that allows it to flow, to form shapes, to sustain life. And all of these interactions, every single one, are guided by something we cannot see, not a force in the everyday sense, not something you can touch or feel directly, but rules, invisible rules that determine how particles behave. There are only a few of these rules, and they're remarkably consistent across the entire universe. One of them gently pulls things together. This is what we call gravity. It is what keeps your body resting against the surface beneath you. What holds the moon in orbit around the Earth? What gathers vast clouds of gas into stars? Another governs the behavior of charged particles. This is the interaction that allows electrons to remain connected to atoms and atoms to form molecules. It is, in a sense, the quiet glue of chemistry. There is also a force that holds the very heart of the atom together, binding protons and neutrons inside the nucleus with incredible strength. Without it, atoms would simply fall apart. And finally, there is a subtle interaction that allows certain particles to transform into others. It plays a quiet role in processes like radioactive decay and the fusion reactions inside stars. 4 interactions, that is all. 4 gentle rules that guide every process in the universe, from the smallest particles to the largest galaxies. And yet, what is perhaps most remarkable is not just that these rules exist, but that they have the particular strength that they do. If the force that binds atoms was slightly weaker, electrons might drift away and stable atoms would struggle to exist. If it was slightly stronger, atoms might cling too tightly, preventing the flexibility needed for chemistry. If gravity were a little different, stars might not form, or they might burn too quickly to allow anything to develop around them. It is as though each of these interactions has been set to just the right level. Not perfectly balanced in the sense of symmetry, but balanced in the sense that they allow complexity to emerge. And this brings us back gently to those quiet numbers we mentioned earlier, because each of these interactions is not just a rule, it is a rule with a strength, and that strength is described by a number that tells gravity how strongly to pull, a number that tells light how fast it moves, a number that determines how tightly electrons are bound to atoms. Without these numbers, the rules of physics would still exist, but they would not produce anything recognizable. They would be like a piece of music without tempo, notes without rhythm, structure without expression. And so, as strange as it may seem, the richness of the universe, the stars, the atoms, the possibility of life, depends not only on the existence of rules, but on the precise values of a few quiet numbers. Numbers that do not explain themselves, numbers that simply are. And when you step back and look at it this way, something almost poetic begins to emerge. Everything you are, everything you see, everything that has ever existed is built from a very small set of ingredients, a few particles, a few interactions, a few numbers, and yet from this simplicity an entire universe unfolds. It is like watching a vast and intricate tapestry, only to discover that it is woven from just a handful of threads that somehow have been arranged in just the right way to create something that can think, feel, and wonder. Something that can lie quietly in the dark, listening to a story about the universe, while being made of it at the same time, and perhaps that is the most curious part of all, that the same simple ingredients that form distant stars are also the ones forming you, quietly holding you together, right now. If you stay with that thought for just a little longer, something quietly profound begins to settle in. Everything you're made of, every atom, every molecule, every tiny interaction, is not just sitting there by chance. It is being guided, not by something visible or tangible, but by a set of rules so consistent, so reliable, that we rarely stop to notice them at all. They are not written in the sky. They do not make a sound, and yet they are everywhere. You could think of them as the grammar of the universe. Just as language needs rules to form meaning, reality needs rules to form structure. Without grammar, words would scatter into noise, and without these underlying rules, particles would drift without pattern, never forming anything stable or recognizable. These rules, what physicists call the fundamental interactions. There are only a few of them, and yet they shape everything. One of them you feel every moment of your life, even if you rarely think about it. It is the gentle pull that keeps you anchored to the surface beneath you. The same pull that guides the moon in its slow orbit and gathers vast clouds of gas into glowing stars. This is gravity. It is in a way the quiet organizer of the cosmos. It does not rush. It does not force. It simply pulls patiently, allowing matter to come together over time. If you imagine a cloud of gas drifting through space, gravity is the whisper that encourages it to gather, to become denser, to eventually ignite into a star. Without it, the universe might remain a thin, diffuse mist, never forming anything solid or luminous. And yet gravity alone is not enough. There is another interaction, one that operates at a much smaller scale, but is no less important. This one governs how charged particles behave. It determines how electrons are held close to atomic nuclei and how atoms connect to form molecules. You might think of it as the quiet glue of chemistry. It allows atoms to share, to bond, to build structures far more complex than themselves. Without it, there would be no water, no air, no living cells, only isolated particles drifting without connection. Then there is a force that works deep inside the heart of the atom itself. It binds together the particles within the nucleus, holding protons and neutrons in an incredibly tight embrace. This interaction is astonishingly strong, far stronger than the gentle pull of gravity, and yet it operates only over very small distances, almost as if it prefers to work quietly, hidden within the smallest spaces. Without it, the nucleus of every atom would fall apart. There would be no stable atoms at all. And finally, there is a more subtle interaction, one that allows particles to transform from one type into another. It plays a role in processes that are less visible to us, but deeply important, like the reactions that power the sun or the slow transformation of certain elements over time. 4 interactions, that is all. And from these 4 simple rules, an entire universe unfolds. But here is where the story becomes more delicate. These interactions do not just exist. They have strengths. Each one operates with a particular intensity, a specific how much that determines how it behaves. And these strengths are not arbitrary in their consequences. Even small changes can ripple outward, altering the entire structure of reality. Imagine for a moment that the interaction responsible for holding electrons near atoms were just a little weaker. Electrons might wander too far from the nucleus, making atoms unstable. Chemistry, as we know it, would begin to dissolve. Now imagine it slightly stronger. Electrons might cling too tightly, preventing atoms from sharing or bonding in flexible ways. Molecules would struggle to form. The rich complexity of chemistry could collapse into something far simpler and far less alive. Or consider the force that binds the nucleus together. If it were even slightly weaker, atomic nuclei might not hold. If it were stronger, the balance inside stars would change, altering how elements are formed. Even gravity, so gentle on human scales, plays a delicate role across cosmic time. If it were stronger, stars might burn quickly and violently, exhausting their fuel before life has time to emerge. If it were weaker, stars might never form at all. Each interaction, in its own quiet way, seems to sit within a narrow range, a range that allows complexity to grow. Not too much, not too little, just enough. And this is where those mysterious numbers return, because the strength of each interaction is described by a number, a value that does not shift from place to place or from moment to moment, a value that appears to be woven into the very fabric of the universe. For example, there is a number that tells us how strongly light and matter interact. It is a small number, often described as being close to 1 part out of a little over 137. Not exactly that value, but close enough to guide the structure of atoms with remarkable precision. There is another number that sets the strength of gravity. It determines how strongly mass pulls on mass, from the smallest particles to the largest galaxies. And there are other numbers still, quietly defining the properties of particles, the behavior of fields, and the structure of space itself. What is striking is not just that these numbers exist, but that they are exactly what they need to be for a universe like ours to unfold. If you imagine adjusting one of them, just slightly, the effects do not remain small. They spread outward, influencing atoms, stars, galaxies, and eventually the possibility of life. It is a bit like tuning a musical instrument. If one string is slightly off, the entire melody begins to change. Not always dramatically at first, but enough that, over time, the harmony is lost. And yet, in our universe, the notes seem to align, not perfectly in a mathematical sense, but in a way that allows structure, stability, and change to coexist. Atoms form but are not rigid. Stars burn but not too quickly. Matter gathers but does not collapse entirely. It is a balance that feels less like a fixed point and more like a narrow path, a path where complexity is possible. And as you rest here listening, perhaps beginning to feel your thoughts soften at the edges, it is worth noticing just how much depends on this quiet balance. The shape of your body, the rhythm of your breath, the warmth of distant stars, all of it guided by a handful of invisible rules, each one carrying just the right strength to allow this moment to exist. Not loudly, not dramatically, but quietly, persistently, holding everything together. As your thoughts continue to drift gently through these ideas, something begins to take shape. Not a clear answer, not a conclusion, but a quiet realization. The universe is not only guided by rules, it is guided by numbers. And these numbers, as simple as they may seem, carry a kind of mystery that has followed physicists for generations. Because while we can describe how the universe behaves with remarkable precision, there is a deeper question that lingers beneath it all. Where do these numbers come from? If you were to open a physics textbook, you would find elegant equations describing motion, energy, light, and matter. These equations are often beautifully structured, almost like carefully composed pieces of music. They tell you how things change, how forces act, how particles move, but there is always something missing, a number. Without it, the equation is incomplete, silent, like a melody without tempo. To make the equation come alive, you must supply a value, a specific number that sets the scale, the strength, the rhythm of what is being described. Take gravity, for example. There is an equation that tells us how strongly two objects pull on each other. It depends on their masses and the distance between them. But this equation also includes a number, a constant, that determines how strong gravity is overall. Without that number, you would know that objects attract each other, but not how much. Not whether the pull is gentle or overwhelming. Not whether stars can form or whether planets can orbit in stable paths. And so, long ago, scientists had to turn to nature itself to find that number. They built delicate experiments, suspended small masses, measured tiny movements, watched how objects responded to each other with extraordinary care. In one famous experiment, a scientist set up a device so sensitive that even the faint pull between small lead spheres could be detected. By observing how these spheres influenced each other, he was able to estimate the strength of gravity. It was, in a sense, an attempt to weigh the world. Not by lifting it, but by listening carefully to how it pulled on itself. And this process, this quiet act of measurement, has been repeated again and again for many of the universe's most important numbers. There is a number that tells us how fast light travels, not just in a poetic sense, but with astonishing precision. Light moves at a speed so great that it can circle the Earth several times in a single second. And yet, that speed is fixed. It does not change. It is woven into the structure of reality itself. There is another number, far smaller, that governs the strange behavior of the quantum world. It sets the scale at which energy comes in tiny, discrete steps. Without it, atoms would not behave as they do. Light would not interact with matter in the familiar ways we observe. And then there is a number that quietly determines how strongly light and matter interact. It is often described as being close to 1 part out of a little over 137, a small number, almost unassuming, and yet it plays a central role in the structure of atoms, in the way electrons orbit, in the very possibility of chemistry. This number puzzled one of the great physicists of the 20th century. He found it everywhere in his equations, shaping the behavior of particles with remarkable consistency. And yet when he tried to derive it, when he tried to understand why it had that value and not another, he found himself at a loss. It could not be calculated, it had to be measured, and so it stood there, quietly, like a number written on the wall of the universe, waiting to be noticed. This is what makes these constants so unusual. In many areas of science, we hope to explain things by breaking them down into simpler pieces. We look for underlying principles, deeper laws, more fundamental reasons. But here, we seem to reach a boundary. The laws of physics can tell us how the universe behaves once these numbers are known, but they do not yet tell us why these numbers have the values they do. It is as if the universe comes with a set of instructions and a list of parameters already filled in. You can read the instructions, you can follow them, but the choices have already been made. And so, the question returns, could these numbers have been different? At first, it might seem like a strange thing to ask. After all, we only have one universe to observe, one set of values, one reality unfolding around us. But science has always been built on gentle imagination, on asking what if and following the consequences. What if gravity were stronger? What if the interaction between light and matter were slightly weaker? What if the tiny number that governs the quantum world were just a little larger? To explore these questions, scientists do something quite remarkable. They build universes, not with matter and energy, but with mathematics and computation. They take the equations of physics and translate them into code. They create simulated worlds, vast digital landscapes where the same rules apply, but the numbers can be adjusted, and then they watch. They let these simulated universes evolve, step by step, as matter gathers, stars ignite, galaxies form, or fail to form. Sometimes the results look familiar. Clusters of stars emerge, galaxies take shape, patterns resembling our own universe begin to appear. But often, something goes wrong. Matter refuses to gather. Stars burn too quickly or not at all. Atoms fail to hold together. Complexity never has a chance to emerge. It is not that these universes are chaotic. They're often perfectly consistent, perfectly lawful, and yet empty, lifeless, silent. And this is where the mystery deepens, because it suggests that the universe we inhabit, this vast unfolding cosmos filled with stars, planets, and life, is not just governed by rules. It is governed by rules with very particular settings that allow something remarkable to happen. Not just structure, not just motion, but complexity. And eventually, awareness. And so, as you rest here, perhaps feeling the quiet rhythm of your breath, it is worth letting that idea settle gently in your mind, that the universe, in all its vastness, depends on a handful of numbers that cannot yet be explained, numbers that must be measured, numbers that somehow have values that allow this moment to exist. And like so many things in science, the deeper we look, the more the answers seem to open into new questions, not louder, not more urgent, but softer, more patient, waiting quietly to be understood. If you let that idea settle for a moment, it begins to feel almost like a quiet shift in perspective. The universe is not just something that follows rules, it is something that behaves as if those rules have been set, not in a dramatic or intentional sense, not necessarily designed but adjusted. As though the universe, in order to unfold the way it does, requires its parameters to fall within a certain range. A narrow range. You might picture it like a musical instrument resting in a quiet room. Before it can produce anything beautiful, it must be tuned. Each string tightened or loosened, not randomly, but carefully, until it resonates just right. Too tight, and the string might snap. Too loose, and the sound becomes dull and unfocused. Somewhere in between, the instrument begins to sing. And in a strangely similar way, the universe appears to require its own form of tuning, not through hands or intention, but through the values of its fundamental numbers. If you imagine turning one of these numbers slightly, even by a small amount, the effects begin to ripple outward. At first, they may seem subtle, barely noticeable, but over time, across the vast scales of the cosmos, those small changes grow into something much larger. Take gravity again, that quiet force that pulls everything together. If its strength were increased just a little, stars would form more easily, but they would also burn through their fuel much faster. Their lives would become short and intense, like brief flashes rather than long, steady sources of light. Planets orbiting such stars might not have enough time to cool, to stabilize, to allow complex processes to unfold. On the other hand, if gravity was slightly weaker, matter would struggle to gather at all. The early universe, instead of forming stars and galaxies, might remain a thin, expanding haze of particles, never quite coming together. No stars, no planets, no places for life to begin. It is a delicate balance, and gravity is only one part of the story. The interaction that governs atoms and chemistry must also fall within a narrow range. It must be strong enough to hold electrons close to atomic nuclei, but not so strong that atoms become rigid and unable to bond in flexible ways. Because chemistry is not just about stability, it is about possibility. It is about atoms forming and breaking bonds, rearranging themselves into new patterns, creating molecules that can store energy, carry information, and eventually become living systems. If this interaction was slightly different, atoms might still exist, but chemistry could lose its richness. The variety of molecules we depend on might collapse into something far simpler, something far less capable of supporting life. Then there is the interaction deep inside the nucleus of the atom, holding protons and neutrons together. If this force were weaker, many atomic nuclei would not remain stable. Elements beyond the very lightest might never form. The periodic table would shrink, losing the diversity needed to build complex structures. If it was stronger, the balance inside stars would shift. The way elements are created through nuclear reactions would change, altering the abundance of the elements we rely on. Even the subtle processes inside stars, the slow fusion of hydrogen into helium, depend on a careful balance. If the conditions were even slightly different, stars might fail to ignite or burn in unstable ways. And so, across all these layers, particles, atoms, stars, galaxies, the same pattern appears again and again, a quiet dependence on precise values, a sensitivity that seems almost surprising. And yet this sensitivity is not chaotic. It does not suggest instability or randomness. Instead, it suggests that the universe behaves like a system where many parts are connected, where changing one piece influences all the others. You might imagine it as a vast, intricate web, each thread connected to countless others. Pull one thread, even gently, and the entire structure shifts. The shape changes, the tension redistributes, patterns emerge or disappear, and in such a web, it becomes difficult to change just one thing without affecting everything else. This is why scientists, when they explore what-if scenarios, often find that even small changes can lead to universes that look very different from our own. Not slightly different, but fundamentally altered. In some cases, matter never gathers into stars. In others, stars form but live too briefly to create the elements needed for complexity. In still others, atoms themselves cannot hold together long enough for chemistry to unfold. And in many of these imagined universes, there is nothing that resembles life at all. Just particles, fields, motion, but no complexity, no structure that builds upon itself, no quiet emergence of awareness. It is not that these universes are broken. They follow their own rules, their own numbers. They're consistent, predictable, and yet empty. And so, when you return your attention to our own universe, something begins to stand out. Not loudly, not as a declaration, but as a quiet contrast. That here, in this particular arrangement of rules and numbers, something different has happened. Stars formed and lived long enough to create heavier elements. Those elements spread through space, eventually becoming part of planets. On at least one of those planets, chemistry became complex enough to support life. And over immense stretches of time, that life became capable of reflection, capable of asking questions about the universe itself. And perhaps, as you lie here, listening, letting your thoughts drift gently between these ideas, you might notice how extraordinary that chain of events is. Not because it is dramatic, but because it is so finely balanced, so dependent on conditions that, even with our current understanding, seem remarkably precise. And yet, there is something important to remember. This does not necessarily mean that the universe was designed for us. It may simply mean that we're observing the universe from within the narrow set of conditions that allow observers to exist. Still, the feeling remains. That quiet sense that the universe, in order to unfold the way it has, required its settings to fall within just the right range, not perfectly tuned like a machine built for a purpose, but tuned enough, balanced enough, to allow something to emerge, something fragile, something temporary, something aware. And as your thoughts begin to soften and the edges of these ideas blur gently into one another, you may find that the question has not disappeared. It has simply become quieter, more patient, like a distant echo waiting to be explored. Why these values? Why this balance? Why this universe? For now, there is no need to answer, only to notice. As these ideas begin to settle, a quieter and perhaps deeper pattern starts to reveal itself. Up to this point, it may have felt as though we were describing a universe made of things, atoms, particles, stars, planets, objects that exist, each with their own properties, quietly sitting within the vastness of space. But if you look just a little closer, that picture begins to shift, because nothing in the universe simply exists on its own. Everything is constantly in relation to something else. Every particle feels the presence of others. Every atom is shaped by the push and pull of forces around it. Every structure, from the smallest molecule to the largest galaxy, is not just a collection of parts, but a pattern of interactions. In a sense, reality is not made of things. It is made of relationships. You might imagine it like a conversation. Words by themselves are just sounds, but when they interact, when they follow patterns, when they respond to one another, they create meaning. A sentence emerges, then a story. And in a similar way, particles by themselves are almost abstract, tiny, elusive, difficult to picture. But when they interact, something richer appears. Structure, form, possibility. Take a simple example. A single electron on its own does not form anything recognizable. It is just a tiny particle carrying a charge, moving, according to the quiet rules of the quantum world. But place that electron near a proton, and something changes. Now there is attraction, a gentle pull that draws them together, allowing them to form the simplest atom, hydrogen. And once atoms exist, they begin to interact with each other. They share electrons, they exchange them, they arrange themselves into molecules, water forms, carbon chains assemble, complex patterns begin to emerge, each one built upon the interactions that came before. And this layering continues. Molecules interact to form cells, cells interact to form tissues, tissues interact to form living organisms. At every level, the same pattern repeats. not just things, but interactions. And what guides all of this, what determines how these interactions unfold, are those same quiet numbers we have been circling around. Numbers that set the strength of attraction and repulsion. Numbers that determine how easily particles bind together or how quickly they drift apart. Numbers that shape the very possibility of structure. If those numbers were different, the interactions would change. And if the interactions change, the structures that depend on them would change as well. It is like adjusting the rules of a dance. If the timing shifts, even slightly, the dancers begin to lose synchronization. Movements that once flowed together become awkward or impossible, and in the universe the dance is constant. Particles are always moving, always interacting, always responding to the invisible rules that guide them. But there is something even more subtle here, because interactions are not isolated, they are interconnected. The way electrons behave depends not only on their own properties, but on the properties of the forces that act on them. The way atoms form depends on both the strength of attraction and the stability of the nucleus. The way stars shine depends on the balance between gravity pulling inward and energy pushing outward. Each layer depends on the others. Each interaction is part of a larger web. And this web is incredibly sensitive. You might imagine touching one point of it, gently adjusting a single connection. The effect would not remain local. It would spread across atoms, across molecules, across stars and galaxies, until the entire structure of the universe is subtly reshaped. This is why the idea of fine-tuning is not just about individual numbers. It is about how those numbers work together. A universe with slightly different values might still have atoms, but perhaps no chemistry. Or chemistry, but no stable stars. Or stars, but no long-term stability. It is not enough for one part to function. The whole system must align. And in our universe, it does. Not perfectly in a rigid sense, but in a way that allows a remarkable balance between stability and change. Atoms are stable enough to persist, but flexible enough to form molecules. Stars are stable enough to shine for billions of years, but dynamic enough to create new elements. Matter gathers into structures, but does not collapse entirely into uniformity. It is a balance that allows complexity to grow, and perhaps, as you rest here, there is something quietly comforting in that idea, that the world around you is not held together by rigid perfection, but by a kind of dynamic harmony, a balance that allows movement, change, and emergence, a balance that allows you to exist. And yet, the deeper you look, the more this harmony begins to raise questions of its own. Because if everything depends on interactions, and interactions depend on numbers, then the nature of reality itself depends on a handful of values that, at least for now, seem to have no deeper explanation. They are not derived, they are not predicted, they are simply measured, written into our equations, observed in experiments, accepted as part of the structure of the universe. And so we find ourselves in a curious position. We understand with great clarity how the universe behaves once these numbers are known. We can predict the motion of planets, the behavior of atoms, the life cycle of stars. But when we ask why these numbers have the values they do, the answer becomes quiet, not absent, but unfinished, like a sentence that has not yet reached its final word. And perhaps that is part of what makes this exploration feel so gentle. There is no urgency here, no need to solve everything at once, only the quiet unfolding of ideas, each one leading softly into the next, from particles to atoms, from atoms to stars, from stars to life, and from life to questions. Questions that do not demand immediate answers, but instead invite you to rest within them, to let them drift, like distant lights in a dark sky. And as your thoughts begin to slow and your attention softens, you may notice that even this question, the question of why the universe works the way it does, is itself part of the pattern, an interaction, a quiet reflection of a universe that through countless layers of structure has become aware enough to wonder about its own nature, and to ask, softly and patiently, why these rules, why these numbers, why this harmony? As these quiet patterns continue to unfold, the story begins to widen. So far we've drifted inward, toward particles, atoms, and the delicate interactions that allow them to exist. But now, gently, the perspective begins to expand outward. Because those same interactions, guided by those same quiet numbers, do not stop at atoms. They scale upward. They shape the stars. And it is inside stars that the universe begins to transform itself in a way that is both subtle and profound. If you imagine the early universe shortly after its beginning, it was a far simpler place than it is now. Vast clouds of hydrogen, the lightest and simplest element, filled space. There were no planets, no complex molecules, no living systems, just hydrogen, drifting quietly through an expanding cosmos. And yet, even in that simplicity, the same invisible rules were already at work. Gravity patiently pulling matter together. Over immense stretches of time, those clouds of hydrogen began to gather. Slowly, almost imperceptibly at first, regions became denser. The pull of gravity strengthened as more material collected, drawing in even more matter. And eventually, something remarkable happened. The pressure and temperature at the center of these gathering clouds became so intense that a new kind of interaction began. Hydrogen atoms, once separate, began to fuse together, not collide randomly, but merge in a way that transformed them into something new, helium. This process, known as nuclear fusion, is the quiet engine of stars, and it depends on a delicate balance. Gravity pulls inward, compressing the core. At the same time, the energy released by fusion pushes outward. If gravity is too weak, the core never becomes hot enough for fusion to begin. The cloud remains dark and cold. If gravity is too strong, the core becomes too intense, and the reactions proceed too quickly, burning through the star's fuel in a brief and unstable burst. But in our universe, there is a narrow range where these forces balance, where a star can ignite and then continue burning steadily for millions or even billions of years. It is within this balance that stars become more than just glowing spheres of gas. They become forges, slow, patient furnaces where new elements are created. At first, hydrogen becomes helium. Then, as the star evolves and conditions change, helium can fuse into heavier elements, carbon, oxygen, and beyond. Each step requires just the right conditions. Not too hot, not too cold, not too fast, not too slow. And each step depends, once again, on those same underlying numbers. Numbers that determine how strongly particles interact. Numbers that control how easily nuclei can come together. Numbers that shape the very possibility of these transformations. Without them, stars might still form, but they would not behave the same way. They might never ignite, or they might burn chaotically, failing to produce the rich variety of elements needed for complexity. And this is where the story becomes quietly personal, because the elements created inside stars are not just distant, abstract things. They are the building blocks of you, the carbon in your body, the oxygen you breathe, the calcium in your bones. All of these were once formed in the heart of a star, forged under immense pressure and temperature, then released back into space when that star reached the end of its life. Some stars fade gently, shedding their outer layers into the surrounding space. Others end in more dramatic events, scattering their material across vast distances. Over time, this enriched material becomes part of new clouds, new stars, new planets, and eventually, in at least one small corner of the universe, it becomes part of something capable of awareness, something capable of reflection, something capable of asking questions about where it came from. And so, the chain becomes clear. From simple particle to atoms to stars to elements to life. A long, quiet sequence of transformations, each one depending on the last, and each one guided by the same underlying framework of interactions and numbers. If any part of this chain were disrupted, even slightly, the outcome would change. If stars did not live long enough, heavier elements would not form. If the processes inside stars were different, the balance of elements would shift, altering the chemistry that follows. If the universe expanded too quickly, matter might never gather into stars at all. Each step depends on a delicate alignment, not just one condition, but many, all working together. And this is what makes the idea of fine-tuning feel so expansive. It is not limited to a single number or a single interaction. It is woven through the entire history of the universe, from the earliest moments after its beginning, through the formation of stars, through the creation of elements, and into the emergence of life, a continuous thread, a quiet consistency. And yet, there is something else worth noticing. Stars are not permanent. Even the most stable stars have finite lifetimes. They burn their fuel slowly, steadily, over billions of years. But eventually that fuel is exhausted. The balance between gravity and outward pressure shifts, and the star changes. Some shrink, some expand, some end in brilliant displays. And over even longer stretches of time, the universe itself continues to evolve. Which raises another gentle question. If the universe allows life to exist through this chain of processes, does it allow it at any time, or only during certain periods? Because just as the universe was once too simple for life, there may come a time when it becomes too quiet, too empty, too dim. And so, as you lie here, perhaps beginning to feel the slow rhythm of your breath, it is worth considering how much of this story depends not only on the right conditions, but on the right moment. That you exist not just in a universe that works, but in a universe that, for now, is still unfolding in a way that allows stars to shine, elements to form, and life to emerge. A universe that is, in its own quiet way, still alive with possibility. As the story of stars gently unfolds, another layer begins to emerge. Not a new force, not a new particle, but something quieter and perhaps more subtle. Time. Not time as you experience it in your daily life, measured in hours and minutes, but time on a cosmic scale. The slow unfolding of the universe itself, stretching across billions of years. Because even if all the conditions we have explored are just right, even if the rules and numbers allow stars to form and elements to exist, there is still another requirement. The timing must be right. You might imagine the universe as a vast stage slowly preparing itself. In the very beginning, shortly after its birth, it was far too simple for life. There were no heavy elements, no complex atoms, no structures beyond the simplest forms of matter, just hydrogen and a little helium. The raw ingredients were there, but the recipe had not yet begun. The first stars had to form. They had to live their lives slowly transforming simple elements into more complex ones. And then, those stars had to end, releasing their newly created elements back into space. Only then could new stars form, stars surrounded by richer material, capable of forming planets, molecules, and eventually something more intricate. This process takes time, not days or years, but billions of years. If you imagine arriving in the universe too early, there would be nothing here for you. No carbon to form the backbone of complex molecules, no oxygen to support processes like respiration, no diversity of elements to build anything beyond the simplest structures. It would be a universe still in its infancy, quiet, empty of complexity. But what if you arrive too late? The universe is not static. It continues to evolve. Stars do not burn forever. Over immense stretches of time, they exhaust their fuel. The brightest stars live fast and die young, while smaller stars burn slowly but eventually fade. As time goes on, the universe becomes dimmer. The large luminous stars disappear. What remains are smaller, cooler stars, and eventually even those begin to fade. The production of new elements slows. The opportunities for new complexity diminish. In the far future, the universe may become a much quieter place, colder, darker, more spread out. And so, there appears to be a window, a period in cosmic history when conditions are just right, not only in terms of physical laws but in terms of timing. A time when enough stars have lived and died to create the elements needed for life. But not so much time has passed that the universe has grown silent and still. You exist within this window, not at the very beginning, not at the very end, but somewhere in between. And this realization brings us gently to an idea known as the anthropic principle. At first, the name may sound complex, but the idea itself is quite simple when approached softly. It suggests that the universe we observe must be compatible with our existence, not because the universe was made for us necessarily, but because we could only ever find ourselves in a universe where conditions allow observers to exist. It is a bit like waking up in a place where the air is breathable and wondering why the air was arranged that way. The answer may not be that the environment was designed specifically for you, but that you could only wake up in a place where breathing is possible, and in the same way, we should not be surprised to find ourselves in a universe that allows life, because if it did not, we would not be here to notice it. But there is something deeper here, because the anthropic principle does not only apply to where we are, but when we are. You are not observing the universe at a random moment in its history. You're observing it during a period when stars still shine, when elements are abundant, when conditions allow for complexity and life. A kind of quiet, cosmic, just in time. And yet, this does not fully remove the mystery. It softens it, perhaps, but does not erase it. Because even if we accept that we must exist in a universe that allows for our existence, we can still ask why such a universe exists at all. Why these rules? Why these numbers? Why this window of time? The anthropic principle does not answer these questions directly. Instead, it offers a different way of thinking. It reminds us that our perspective is not neutral. We are not outside observers, looking at the universe from a distance. We are part of it, embedded within it, shaped by the very conditions we're trying to understand. And so, our observations are filtered by our existence. We see a universe that works because we are here to see it. But this idea, while gentle, can feel a little unsettling, because it suggests that what we perceive as special or finely balanced might not be unique in a broader sense. It might simply be one of many possibilities, one that happens to allow us to exist. Still, even within this perspective, something remains quietly remarkable. That the universe, in its long and patient unfolding, has reached a stage where it can be observed. That somewhere within its vastness, matter has arranged itself into forms capable of awareness, capable of reflection, capable of asking questions about time, about existence, about the nature of reality itself, and that you, here and now, are part of that unfolding, not separate from it, but a continuation of it, a moment in which the universe becomes aware of its own history, its own timing, its own delicate balance. And as you rest here, perhaps feeling the gentle rhythm of your breathing, you might notice how this idea does not demand urgency. There is no need to resolve it, no need to reach a final answer, only to sit with it, to let it drift, like a thought carried softly through the night, that you exist not only because the universe allows it, but because you arrived at a moment when it could happen. A quiet intersection of time and possibility, a brief window in an immense cosmic story. And within that window, this moment. As the idea of timing settles gently into the background, another layer of balance begins to reveal itself. Not the balance of when things happen, but the balance of how they continue. Because it is one thing for a star to form. It is something else entirely for a star to remain stable. If you imagine a star from a distance, it may appear calm, a steady glow in the night sky, unchanging, almost eternal. But beneath that quiet light, something far more dynamic is taking place. A constant negotiation, a quiet tension between opposing forces. At the heart of every star, gravity is always at work. It pulls inward, drawing all of the star's mass toward its center. If gravity were left alone, it would compress the star further and further, increasing the pressure and temperature in its core. But there is another process happening at the same time, nuclear fusion. As atoms are pushed together under immense pressure, they begin to combine, releasing energy in the process. This energy does not remain hidden. It pushes outward, creating pressure that resists the inward pull of gravity. And so, the star exists in a delicate state of balance, gravity pulling in, energy pushing out, neither side winning, neither side collapsing, a kind of cosmic equilibrium. If you imagine this balance as a breath, it is as though the star is constantly inhaling and exhaling at the same time, a steady rhythm, sustained over millions or billions of years. And this balance depends once again on the precise values of those underlying numbers. If gravity were just a little stronger, the inward pull would increase. The core would compress more tightly, raising the temperature and accelerating the rate of fusion. The star would burn its fuel more quickly, shortening its life. It would shine brighter, but for a much shorter time. If gravity were slightly weaker, the opposite would occur. The core might not reach the temperatures needed for fusion to begin at all. The star would remain a dark, cold object, never igniting. And so, there is a narrow range. A range where stars not only form but live long enough to sustain the processes that lead to complexity. But gravity is not acting alone. The behavior of the particles inside the star also depends on the interactions that govern atomic and nuclear processes. The ease with which atomic nuclei combine, the stability of those nuclei, and the way energy is released. All of these depend on the same quiet constants we have been exploring. For example, the process that allows hydrogen to fuse into helium requires a very specific set of conditions. It is not an easy reaction. In fact, it is surprisingly slow. And this slowness is not a flaw, it is a feature. Because if fusion happened too easily, stars would burn through their fuel almost instantly. If it were too difficult, fusion might never begin. The rate at which this process occurs is finely balanced, allowing stars like our Sun to shine steadily for billions of years, long enough for planets to form, long enough for environments to stabilize, long enough for life to emerge and evolve. And this balance extends beyond individual stars. Across the universe, stars come in many sizes and lifetimes. Some are massive and short-lived, burning brightly and ending quickly. Others are smaller and longer-lived, providing steady energy over immense stretches of time. This diversity is important. It allows for a range of environments, a variety of conditions, and a richness of possibilities. But even within this diversity, there are limits. If the underlying constants were different, the range of possible stars might shrink. There might be no long-lived stars at all, or only stars that burn too faintly to support complex processes on surrounding planets. And without long-lived stable stars, the chain we explored earlier begins to break. No steady source of energy, no time for chemistry to become complex, no gradual unfolding of life. And so, once again, the pattern returns. A quiet dependence on balance. Not perfect balance in the sense of symmetry, but balance in the sense of sustainability. A balance that allows processes to continue, to unfold slowly, to build upon themselves over time. You might think of it like a fire. If a fire burns too quickly, it consumes its fuel and dies out. If it burns too weakly, it may never fully ignite. But when the conditions are just right, the fire can sustain itself. It can continue steadily, providing warmth and light over time. Stars are like that, but on a scale that is almost beyond imagination. And yet, the principle is the same. A balance between forces, a balance between rates, a balance between extremes. And as you rest here, perhaps feeling the quiet rhythm of your own breath, there is something gently familiar about this idea. Because balance is not only found in stars, it is found in many aspects of life. In the way your body regulates itself, in the way ecosystems maintain stability, in the way systems, both natural and human-made, depend on a careful interplay of forces. Too much in one direction, and things begin to break. Too little, and they fail to function. Somewhere in between, there is a range where things can continue, where complexity can grow, where life can exist. And it is within this range that stars live their long, steady lives. Lives that are not permanent, but are long enough, stable enough, predictable enough, to support everything that follows. Planets forming from the material around them, atmospheres developing, chemistry unfolding, and eventually, in at least one small corner of the universe, something capable of awareness emerging. And so, the quiet glow of a star is not just a distant light. It is a sign of balance, a sign that for now the conditions are right, that the inward pull and the outward push are in harmony, that the universe in this moment is still in that delicate state where complexity can exist, where life can unfold, and where, somewhere beneath the light of a star, a mind can wonder about it all. As the steady rhythm of stars fades gently into the background, a different kind of question begins to rise, not about what the universe is, but about what it could have been. Up to this point, we have followed the thread of how things work, how particles interact, how atoms form, how stars shine, and how, over time, complexity emerges. And along the way, we have noticed that each step depends on a delicate balance, a balance guided by a handful of numbers. Now, imagine something very simple. Imagine taking just one of those numbers and changing it. Not dramatically, just a little, a small adjustment, almost too small to notice at first glance. What would happen? At first, it might seem like the effects would also be small. A slight shift here, a subtle difference there. But the deeper scientists have explored this question, the more surprising the answer has become. Because the universe is not a collection of isolated parts, it is a deeply interconnected system. And in such a system, small changes do not always stay small. They can spread, they can amplify, they can reshape everything. You might picture it like a vast web stretching across space and time, each thread connected to countless others, each point depending on the tension of the entire structure. If you touch one thread, even gently, the movement travels outward. It reaches distant parts of the web, altering the pattern in ways that are not always easy to predict. In the universe, those threads are the interactions between particles, atoms, and forces, and the tension in those threads is set by the values of the constants. Change one value, and the entire web begins to shift. Consider for a moment the strength of gravity. It is often described as the force that pulls matter together, but its influence goes far beyond simple attraction. It shapes the formation of stars, the motion of galaxies, and the large-scale structure of the universe. If gravity were increased by even a modest amount, matter in the early universe would gather more quickly. Stars would form sooner, but they would also evolve faster. Their lifetimes would shorten, and the balance inside them would shift. Instead of long-lived stars gently producing elements over billions of years, you might have brief, intense bursts of activity. A universe that burns brightly, but fades quickly. Now imagine reducing the strength of gravity. Matter would drift more freely, less inclined to gather. The early universe might remain a diffuse cloud, expanding without ever forming the dense regions needed for star formation. No stars, no galaxies, just a thin, quiet fog of particles stretching endlessly through space. And this is only one number. If you turn your attention to the interaction that governs atoms and chemistry, the consequences become just as striking. This interaction determines how tightly electrons are held near atomic nuclei, and how atoms bond with one another. If it was slightly weaker, electrons might not remain bound to atoms as easily. The stability of atoms would be compromised, and the formation of molecules would become difficult. Chemistry, as we know it, would begin to unravel. If it was slightly stronger, electrons might cling too tightly, reducing the flexibility needed for atoms to share and rearrange themselves. Molecules might still exist, but their variety and complexity could be greatly reduced. And without rich chemistry, the path to life becomes far less likely. Even deeper within the atom, the force that holds the nucleus together plays a critical role. This interaction binds protons and neutrons in a delicate balance. If it were weaker, many nuclei would fall apart, limiting the range of elements that can exist. If it was stronger, the processes inside stars would change, altering how elements are formed and distributed. In each case, a small adjustment does not lead to a slightly different universe. It leads to a fundamentally different one. And what makes this even more intriguing is that these changes do not act independently. They overlap, they interact. Changing one constant influences the effects of others, creating a complex landscape of possibilities. This is why scientists often explore these questions through careful calculations and simulations. By adjusting one parameter at a time, or sometimes several, they can begin to map out what kinds of universes might be possible. And what they find is both fascinating and, in a quiet way, humbling. Many of these possible universes are not chaotic or unstable. They follow consistent rules. They evolve according to their own internal logic, and yet, they do not lead to complexity. They do not produce stars that live long enough. They do not create the diversity of elements needed for chemistry. They do not allow the slow unfolding of structures that eventually give rise to life. They are, in a sense, complete, but empty, and this realization begins to shift the perspective once again, because it suggests that the universe we inhabit is not just one of many possibilities, it is one of the very few where a long chain of conditions aligns. A chain that stretches from the smallest particles to the largest cosmic structures. A chain where each link depends on the others, and where even a small change can cause the entire sequence to break. It is like a long line of dominoes, carefully arranged, each one placed at just the right distance from the next. If the spacing is slightly off, the chain reaction may fail. The sequence stops before it can unfold. But when everything is aligned, the motion continues, each step leading naturally to the next. And in our universe, that sequence has unfolded. Particles formed atoms, atoms formed stars, stars created elements, elements formed planets, and on at least one of those planets, conditions allowed life to emerge. Not as an inevitable outcome, but as a possibility that required everything before it to work together. And as you rest here, letting these ideas settle, there is something quietly remarkable in that realization, that the universe is not just governed by rules, but by rules that must work together in a very particular way. That changing even a single number, even slightly, can reshape the entire structure of reality. And yet here, in this universe, the numbers align. Not perfectly, not without mystery, but in a way that allows this moment to exist, this breath, this thought, this quiet awareness. And perhaps, as your thoughts begin to slow, you might notice how this question, this exploration of what if, does not lead to a sense of instability, but to a deeper appreciation of what is. Not because it had to be this way, but because, somehow, it is. If you let your thoughts drift back to the smallest scales we explored earlier, to those quiet building blocks of reality, something very delicate begins to come into focus. Atoms, simple, familiar, almost taken for granted, and yet everything you know, every object, every surface, every breath depends on their quiet stability. An atom is not a solid object in the way it might appear in a diagram. It is more like a small dynamic system. At its centre, a dense nucleus. Around it, a soft cloud of electrons, moving in ways that are not fixed paths, but gentle probabilities. A kind of presence rather than a precise location. And this system, as subtle as it is, depends on a balance. The electrons are drawn toward the nucleus, held close by an invisible attraction. At the same time, their motion prevents them from collapsing inward completely. It is a quiet negotiation between attraction and motion, a balance that allows the atom to exist. Now, imagine changing something very small, not the structure itself, not the rules, just one number. The number that helps determine how much an electron responds to the forces around it. A number that is tied in part to what we describe as the mass of the electron, the way it carries inertia, the way it moves when influenced. If that number were slightly larger, the behaviour of the electron would begin to change. It would move differently, respond differently. Its motion around the nucleus would become tighter, faster, less flexible. At first, this might not seem dramatic. The atom would still exist. The electron would still remain near the nucleus, but the change would not stop there. Because atoms do not exist in isolation. They interact. They share electrons. They form bonds. And it is in these interactions that the consequences begin to unfold. If electrons are too tightly bound, atoms lose their ability to share them easily. The subtle dance that allows atoms to connect, to form molecules, becomes restricted. Imagine trying to link hands with someone, but your arms are held too tightly at your sides. Connection becomes difficult, movement becomes limited, and in the universe this limitation would ripple outward. Molecules would struggle to form. Those that do might be rigid, unable to rearrange or adapt. The rich, flexible chemistry that allows for complexity, the kind that leads to life, would fade into something far simpler. Now imagine the opposite. The electron's behaviour shifts in the other direction. It becomes easier for it to drift away from the nucleus, less tightly held, more easily influenced. Again, the atom might still exist, but now it is less stable. The electron cloud becomes more diffuse, more uncertain, less anchored. Atoms would struggle to hold on to their electrons. Bonds between atoms would weaken. structures that depend on stable connections would begin to fall apart, and once again the effects would spread. No stable molecules, no long chains of carbon, no intricate structures capable of storing information or carrying energy. The foundation of chemistry would begin to dissolve, and with it, the possibility of life as we know it. What is striking here is not just that atoms depend on this balance, but that the balance is narrow. There's not a wide range of values that produce rich, flexible chemistry. There is a window, a small region where atoms are stable enough to persist, but flexible enough to interact, where electrons are held close, but not too tightly, where bonds can form and break and form again. This constant reshaping is essential, because life is not static. It depends on change, on reactions, on the ability of molecules to rearrange themselves to respond to their environment, to build and rebuild continuously. Without this flexibility, even if atoms existed, the path to life would be blocked. The universe would remain simple, quiet, unchanging. You might picture it as a vast space filled with isolated particles, each one drifting gently, occasionally interacting, but never forming anything that lasts. No flowing water, no complex structures, no living systems, just a kind of stillness, a universe where the ingredients exist, but the recipe cannot unfold. And this brings us back, once again, to that quiet idea of fine-tuning, because the stability of atoms is not guaranteed by the existence of physical laws alone. It depends on the values of the numbers that shape those laws, numbers that determine how strongly particles interact, numbers that set the scale of motion and attraction, numbers that, if changed even slightly, can transform a universe filled with structure into one that remains forever simple. And yet, here, in this universe, atoms do exist. They form easily, they persist, they combine in countless ways, creating the vast diversity of matter we observe, from the air around you to the cells within your body, from the oceans to the distant stars, all of it built upon this quiet balance. And as you rest here, perhaps letting your thoughts soften, there is something gently humbling in that realization, that the solidity of the world around you, the stability of your own body, depends on a balance so delicate it could easily have been otherwise. And yet, it is not. The electrons remain, the atoms hold together, the bonds form and reform, quietly, continuously, allowing everything else to follow. As the quiet stability of atoms settles into the background, the story gently expands once more, because even if atoms can exist, even if chemistry can unfold, there is still another step required before anything like life can begin. Energy, not in sudden bursts, not in fleeting flashes, but in a steady, reliable form, a source that can persist long enough for complexity to grow. And in our universe, that source is the star. From a distance, a star may seem simple, a point of light, steady and calm. But as we've seen, that calmness hides a delicate balance, a balance that allows stars to form, to shine, and to endure. Now imagine a universe where that balance is disturbed, not entirely broken, just shifted. Once again, we turn to a single idea. What if the strength of gravity were different? Gravity is the quiet force that gathers matter. It draws clouds of gas together, allowing them to become dense enough for stars to form. Without it, matter would drift, spreading out into an ever-thinning mist. If gravity were slightly weaker, this gathering would struggle to begin. Clouds of hydrogen would expand and disperse, never becoming dense enough to ignite. The universe would remain filled with gas, but that gas would never transform into stars. No stars means no steady light, no steady heat, no long-term source of energy to support anything more complex. It would be a universe that is not chaotic, but quiet. A dim, diffuse expanse where matter exists but never comes together. Now imagine the opposite. Gravity, slightly stronger. At first, this might seem like it would help. Matter would gather more easily, collapsing into stars more quickly. The universe might fill with bright, massive stars. But this ease comes with a cost. When gravity is stronger, the collapse of matter becomes more intense. The cores of stars become hotter, denser, more extreme. Fusion reactions speed up. The star burns through its fuel faster. Instead of long, steady lifetimes, stars become brief and violent. They flare brightly and then fade. In such a universe, stars might exist, but only for short periods. Too short for planets to form and stabilize, too short for complex processes to unfold, and in some cases gravity might dominate so strongly that matter collapses beyond the point of forming stars at all. Instead, it forms something else. Black holes, regions where gravity becomes so intense that nothing can escape, not even light. In a universe where gravity is too strong, much of the available matter might be drawn into these dense regions early on, locking away the raw material needed for stars, for planets, for life. The universe would still have structure, but it would be a very different kind of structure. Dark, dense, and largely inaccessible. And so, between these two extremes, too gentle and too overwhelming, there exists a narrow range. A range where gravity is strong enough to gather matter, but not so strong that it consumes it entirely. A range where stars can form and continue, where they can shine steadily, providing energy over billions of years. This steady shining is not just a detail, it is essential, because life, as we understand it, does not arise instantly. It unfolds slowly. Chemical processes build upon one another, structures grow in complexity, systems develop, adapt, and evolve. All of this takes time, and time requires stability. A star that flickers briefly cannot support that process. A star that burns too weakly cannot provide enough energy. It must be just right. Not perfect in a precise mathematical sense, but within a range that allows for continuity. And this continuity depends, once again, on the values of those quiet numbers. The number that determines how strongly gravity pulls. The numbers that govern how energy is produced inside stars. The numbers that shape how matter behaves under extreme conditions. Each one contributing to a balance that allows stars to exist as long-lived sources of light and heat. And as you rest here, perhaps imagining a sky without stars, you may notice how much of our experience depends on their quiet presence. The warmth of sunlight, the cycle of day and night, the energy that flows through ecosystems, sustaining life in countless forms. All of it begins with the steady light of a star. Now imagine a universe without that light, a universe where the sky remains dark, where no distant points of brightness mark the passage of time, where energy is scattered, inconsistent, unable to support anything lasting. It would not be chaotic, it would not be violent, it would simply be still. A universe where the ingredients exist, but the process never begins. And this, once again, returns us to that quiet idea of fine-tuning. Because the existence of stars is not guaranteed. It depends on a balance between forces, a balance between gathering and dispersing, between collapse and stability, between too little and too much. And in our universe, that balance exists. Stars form, they shine, they endure, long enough for everything else to follow. And as your thoughts begin to slow and the idea of distant stars softens into something more abstract, you may find yourself returning to a familiar question. Not loudly, not urgently, but gently. Why this balance? Why these values? Why a universe where stars can shine long enough for you to be here, beneath their light? As the quiet glow of stars fades gently into the background, another influence begins to emerge, one that is far less visible, less intuitive, and yet just as important. It is not something that pulls things together like gravity. It is something that does the opposite. It gently, but persistently, pulls everything apart. You might imagine space itself, not as an empty stage where events unfold, but as something active, something that can stretch, something that can expand. And in our universe, it does. If you could step far outside and watch the universe over immense stretches of time, you would see galaxies drifting away from one another. Not because they are moving through space like objects in a room, but because the space between them is slowly growing, stretching, carrying them apart. This expansion is not uniform in its effects. On small scales, gravity still holds things together. Galaxies remain intact. Stars continue to orbit within them. Even planets remain bound to their stars. But on the larger scales, the expansion dominates, and behind this expansion lies something we do not fully understand. A kind of energy associated with space itself, often described simply as a tendency for space to expand, a gentle push that becomes more noticeable over time. Now, imagine adjusting this effect, not removing it, just increasing it slightly. At first, the change might seem subtle. The universe would still expand, galaxies would still move apart, but the rate of expansion would be faster, and that difference, though small at the beginning, would grow, because expansion compounds over time. The more space stretches, the faster it can continue to stretch. And if this expansion becomes too strong, something important begins to break. The early universe, after its beginning, was a place where matter needed time to gather. Gravity had to draw particles together, forming the first dense regions. Those regions would become stars, galaxies, and eventually the structures that support life. But if space expands too quickly, gravity does not have enough time. Matter begins to separate faster than it can gather. Clouds of gas stretch apart before they can collapse. The seeds of galaxies never take root. And without galaxies, there are no stars. Without stars, there are no heavy elements. Without those elements, there is no chemistry capable of building complexity. The universe remains filled with particles, but those particles never come together. You might picture it like trying to gather a handful of sand while standing on a surface that is slowly pulling away beneath your feet. No matter how gently you try to bring the grains together, the distance between them keeps increasing. The structure cannot form. And this effect does not need to be extreme. Even a modest increase in the rate of expansion could prevent galaxies from forming. A universe that might otherwise have been filled with stars could instead remain a vast, diffuse expanse, cold, dark, and largely empty. Now, imagine the opposite. If this expansive effect were weaker, gravity would have more time to act. Matter would gather more easily, forming structures more quickly. At first, this might seem beneficial, but as with all things in this delicate balance, too much in one direction can lead to new problems. If matter gathers too quickly, structures may form in ways that are too dense, too chaotic. The evolution of galaxies could change, altering the environments in which stars and planets form. Once again, the balance is narrow. Not a single precise point, but a range where expansion and gravity coexist, where space stretches, but not so quickly that it prevents structure, where matter gathers, but not so rapidly that stability is lost. And within this range, something remarkable happens. Galaxies form. Not immediately, not everywhere, but gradually. Over time, clusters of stars emerge, each one a small island of light within the vastness of space. And within those galaxies, the processes we explored earlier begin to unfold. Stars ignite, elements are forged, planets take shape, and eventually, in at least one of those countless systems, conditions allow for life. But without this balance, without the expansion of space being just right, none of that would occur. The universe would still exist, it would still follow its rules, but it would remain unstructured. A place where particles drift, where distances grow, and where nothing ever gathers long enough to become something more. And as you rest here, perhaps imagining the quiet stretching of space itself, there is something almost calming in the idea, not because it is simple, but because it is so gradual, so patient. The universe does not rush. It unfolds slowly, over billions of years, guided by forces that are gentle on human scales, but profound over cosmic time. And within that unfolding there is a balance between expansion and attraction, between separation and gathering, between the tendency of things to drift apart and the tendency of things to come together. And it is within that balance that everything we know has emerged. Stars, galaxies, planets, life, and even the quiet awareness that allows you to consider these ideas now. And so, once again, the pattern returns. Not as a conclusion, but as a quiet observation, that the universe, in order to become what it is, depends on a set of conditions that must fall within a certain range. Not too fast, not too slow, just enough. Enough for matter to gather, enough for structure to form, enough for complexity to grow. And as your thoughts begin to soften and the idea of expanding space drifts gently into the background, the question remains, not pressing, not urgent, but quietly present. Why this balance? Why a universe that expands, but not so quickly that nothing can ever come together? As these possibilities begin to gather in your mind, something quieter begins to emerge. Not a single change, not just one number shifting, but many, all at once. Imagine for a moment stepping back and looking not at one universe, but at many possible ones, each following its own set of rules, each guided by its own values, each unfolding in its own way. Some of these universes might look familiar at first glance. Particles would exist, forces would act, motion would unfold according to consistent patterns. But as time passes, the differences would begin to show. In one universe, atoms never quite settle. Electrons drift too loosely, unable to form stable bonds. Matter exists, but it never gathers into anything lasting. In another, atoms are too rigid, their internal balance too tight, their interactions too limited. Molecules struggle to form, and when they do, they remain simple, unable to build complexity. In yet another, gravity pulls too strongly. Matter collapses quickly, forming dense regions where light cannot escape. The universe becomes dominated by dark, compact structures, leaving little room for the slow unfolding of stars and planets. And in another still, space itself stretches too rapidly. Matter drifts apart before it can gather. The seeds of structure never take root. Galaxies never form. Each of these universes is not chaotic. They are not broken. They follow their own rules, their own internal logic. They are consistent. And yet, something is missing. Structure, complexity, the long chain of interactions that leads from particles to atoms, from atoms to stars, from stars to life. In many of these universes, that chain never begins, or it begins and then stops. Too early, too quickly, before anything can build upon what came before. You might imagine standing in one of these universes. There is no sound, not because sound cannot exist, but because there is nothing to carry it. No atmosphere, no movement, no processes unfolding. There is no light from distant stars because no stars have formed, no warmth, no cycles, no change, just a vast quiet stillness, a universe that exists but does not become. And as you move through these imagined possibilities, a pattern begins to take shape. It is not that our universe is the only one that could exist. It is that among the many ways a universe might unfold, most do not lead to complexity. Most do not lead to structure. Most do not lead to anything that could be described as life. They remain simple, sparse, unchanging. You might think of it as an ocean of possibilities, a vast expanse where countless universes drift, each one following its own path. And within that ocean, only a very small number allow something more to emerge, something that builds upon itself, something that evolves, something that becomes aware. And our universe appears to be one of those rare cases, not necessarily designed, not necessarily intended, but aligned in just the right way, not perfectly, not without mystery, but enough. Enough for atoms to form, enough for stars to shine, enough for galaxies to gather, enough for life to appear, and enough for that life to look outward and wonder. This realization can feel both profound and strangely calming, because it does not demand that the universe be perfect. It does not require that everything be precisely tuned in an absolute sense. It only suggests that, among many possibilities, there are some where complexity can arise, and we find ourselves in one of them. Still, there is a quiet weight to this idea, because it shifts the way we think about existence. It suggests that what we experience as natural, as expected, may in fact be quite unusual. That the stability of atoms, the light of stars, the structure of galaxies, these things that feel so fundamental, may not be common at all. They may be rare outcomes, fragile alignments, moments of possibility within a much larger space of silence. And yet, here they are, here you are, in a universe where these alignments hold, where the chain of events has unfolded without breaking, where complexity has had time to grow, and where awareness has emerged. And as you rest here, perhaps feeling the quiet rhythm of your breath, there is something gently grounding in that thought. Not because it answers every question, but because it frames them differently. Instead of asking only why the universe is the way it is, we begin to ask how many ways it could have been otherwise, and how many of those ways would have remained silent, still, empty, a universe where nothing gathers, nothing forms, nothing begins. And in that contrast, something becomes clear, not loudly, not as a conclusion, but as a quiet observation, that the universe we inhabit is not just a collection of rules and numbers. It is a particular arrangement of them, an arrangement that allows something to happen, something fragile, something temporary, something aware. And as your thoughts begin to soften, drifting gently between these possibilities, the idea settles that most universes, if they exist at all, would remain quiet, empty, still, and that this one, for reasons not yet fully understood, is not. As that quiet image of a silent universe begins to fade, another thought slowly takes its place, a question that feels almost personal. If most universes are empty, if complexity is rare, if everything we know depends on such delicate conditions, does that make us special? At first, it might seem that way. After all, you exist in a universe where atoms hold together, where stars shine steadily, where time has unfolded just long enough for life to emerge. It can feel as though everything has aligned to make this moment possible. But there is another perspective, a quieter one that has shaped our understanding of the universe for centuries. It begins with a simple idea that we are not at the center of things. Long ago, it was natural to imagine that everything revolved around us, that the Earth was the centre of the cosmos, and that the stars moved across the sky for our benefit. It felt intuitive, comforting. But over time, that view began to change. Observations grew more precise, patterns became clearer, and slowly, the idea that we were at the centre began to dissolve. The Earth was not the centre of the universe. It was one planet, orbiting one star among many. And that star, in turn, was not special. It was one among billions in a vast galaxy. And that galaxy itself was not unique. It was one among countless others, stretching across a universe so large that its full scale is still difficult to comprehend. This shift in perspective is often described as the Copernican principle. Not a rule written into physics, but a way of thinking. A reminder that we should not assume we occupy a special or privileged position in the cosmos, that what we observe here may not be unique, and that our place in the universe may be more ordinary than it feels. At first, this idea can feel unsettling, because it gently removes the sense of centrality. It suggests that we are not the focus of the universe, but a small part of it, a brief moment in a much larger story. And yet, when we return to the idea of fine-tuning, something interesting happens. Because while the Copernican perspective tells us that we are not special in terms of location, the conditions around us still appear remarkably well suited for life. The numbers align, the balance holds, the timing works, and this creates a kind of tension. On one hand, we are not at the centre, not uniquely placed, not the focus of the universe, but on the other hand, the universe we observe seems to allow for our existence in a very specific way. It is as if we are both ordinary and fortunate, not singled out, but somehow present. And this leads to a gentle shift in how we think about the question. Instead of asking, is the universe designed for us? We begin to ask, what does it mean that we're here at all? Because the Copernican idea does not deny the complexity of the universe. It does not deny the delicate balance we've been exploring. It simply reminds us to be cautious, to avoid assuming that this balance exists because of us. Instead, it suggests that we are observers within a system that follows its own rules, a system that does not change in response to our presence. The stars do not shine for us. Gravity does not pull for us. The laws of physics do not adjust themselves to accommodate our existence. They simply are, and we find ourselves within them. This perspective can feel humbling, but it can also be calming, because it removes the need for the universe to have intention. It allows it to be what it is, a vast unfolding structure governed by consistent rules, evolving over immense stretches of time. And within that structure there is space for complexity to emerge, space for life, space for awareness. Not as a guaranteed outcome, but as a possibility that has been realized, at least here. And perhaps as you rest here, letting these ideas settle, you might notice how this perspective shifts the feeling of the question. It becomes less about purpose and more about presence, less about why everything was arranged, and more about the fact that it works. That, in this universe, under these conditions, something has emerged that can reflect on its own existence. And that reflection does not require the universe to care. It does not require intention or design. It simply requires that the conditions allow it. And they do. Not everywhere, not always, but here and now. And as your thoughts begin to soften, there is something quietly grounding in that realization that you're not at the center of the universe, but you are part of it, not separate from it, but formed by the same processes that shape stars and galaxies. And in that sense, the question of whether the universe cares begins to fade, because the universe does not need to care. It only needs to be, and somehow that is enough. As that sense of not being at the centre begins to settle, another idea quietly rises to meet it, an idea that does not contradict what we have explored, but reframes it. Softly, patiently, it begins with a simple observation. You are here. Not as an abstract concept, not as a distant possibility, but as a real, immediate presence, breathing, thinking, listening. And because you are here, certain conditions must be true. The air around you must be breathable. The temperature must fall within a range that allows your body to function. The chemistry that supports life must be stable. None of these things are guaranteed everywhere, and yet they are true here. Now imagine waking up in a room. You open your eyes, and the air is comfortable. The temperature is gentle. Everything feels just right for you to exist. You might ask, why is this room perfectly arranged for me? But there is another way to think about it. Perhaps the room is not arranged for you. Perhaps you are simply in one of the rooms where you can exist. In all the other rooms, those without air, without the right conditions, you could not wake up at all. So you never find yourself there. This is the essence of what is known as the anthropic principle, not a law of physics, not a statement about design, but a way of understanding observation. It suggests that when we look at the universe, we must remember that our perspective is shaped by the fact that we are here to observe it. We do not see all possible universes. We do not experience all possible conditions. We only experience the ones that allow observers like us to exist. And so, it should not be surprising that the universe appears compatible with life, because if it were not, we would not be here to notice it. This idea can feel almost too simple at first, almost like it avoids the deeper question. But if you sit with it for a moment, it begins to shift something subtle in the way we think. It reminds us that observation is not neutral. We're not outside the universe, looking in. We're part of it, embedded within it, shaped by its conditions. And so, what we observe is filtered through our own existence. We see a universe where atoms are stable, because unstable atoms would not allow us to exist. We see a universe where stars shine steadily, because without that steady light, life would not emerge. We see a universe where the balance of forces allows complexity, because without that balance, there would be no one to notice the imbalance. In this way, the anthropic principle does not explain why the universe has its particular values. It explains why we observe those values. It is not a statement about the universe itself, but about the relationship between the universe and the observer. And this distinction is important, because it prevents us from drawing conclusions too quickly. It reminds us that the appearance of fine-tuning may be, at least in part, a reflection of our position within the system, like a fish noticing that water surrounds it. The fish might wonder why water exists in just the right way to support its life. But from a broader perspective, it is not that water was created for the fish. It is that the fish exist in an environment where water is present, and if it were not, the fish would not be there to ask the question. Still, even with this perspective, something remains unresolved. Because the anthropic principle tells us why we observe a life-permitting universe, but it does not tell us why such a universe exists at all. It does not explain why the constants have the values they do. It does not explain why the balance falls within the narrow range that allows complexity. It simply tells us that, given our existence, we should not be surprised to observe such a universe. And so, the question shifts again from why is the universe perfect to something quieter. Given that we are here, what does that tell us about the kind of universe we must be in? It is a subtle shift, but an important one, because it moves the focus away from assumptions about intention and toward an understanding of selection. Not selection in the sense of choice, but in the sense of filtering. We observe a universe that works, because only such a universe can be observed by beings like us. And yet, even as this idea settles, there is still a sense that something deeper remains. Because while the anthropic principle explains why we see what we see, it does not remove the mystery. It does not explain the origin of the rules, or the origin of the numbers, or the reason why the universe allows for this narrow window of possibility at all. It simply tells us that, from within that window, the view will always look consistent. And perhaps, as you rest here letting these thoughts drift gently through your mind, there is something calming in that realization, that the universe does not need to be perfectly designed. It only needs to allow for the conditions in which observation is possible. And within those conditions, everything else unfolds. Atoms form, stars shine, life emerges, and awareness appears, not as a necessity, but as a possibility that has been realized. And you, here and now, are part of that realization, not outside it, not separate from it, but shaped by it. A quiet expression of a universe that, in at least one small corner, has become capable of noticing itself. And as that idea settles, gently, like a thought fading into the background, the question remains. Not louder, not more urgent, but softer, more patient. If we can only observe universes that allow us to exist, how many others might there be that we will never see? As that quiet question lingers, how many other universes might exist, unseen and unreachable? Your thoughts begin to drift outward once more, not just across space, but across possibility itself. Because if the universe we observe is only one arrangement of rules and numbers, it is natural to wonder whether there could be others, other versions, other combinations, other ways for reality to unfold. This idea is often described as the multiverse, not a single clearly defined theory, but a collection of possibilities. Different ways of imagining that what we call the universe might be only a small part of something much larger. A vast landscape of universes, each with its own properties, its own constants, its own story. You might picture it like an endless field of bubbles, each bubble a universe, each one expanding, evolving, following its own internal rules. Some bubbles may look similar to ours, others may be profoundly different. In some, the forces that shape matter might be stronger or weaker. In others, the balance of expansion and gravity might shift in ways that prevent structure from forming. And in many of these bubbles, nothing much happens at all. No stars, no galaxies, no complexity, just quiet expansion, stillness. And within this vast collection, there may be a small number of universes where the conditions happen to align, where the numbers fall within the narrow range that allows atoms to form, stars to shine, and life to emerge. In this view, our universe is not unique in a purposeful sense. It is simply one of the many that work. One of the many where the long chain, from particles to awareness, can unfold without breaking. You might think of it like rolling a set of dice. Each roll produces a different outcome. Most combinations are ordinary. Some are less useful. And a few, rare combinations allow something special to happen. If you roll enough times, eventually those rare combinations will appear. Not because they were intended, but because they are possible. And if you happen to exist in one of those rare outcomes, it may feel as though everything has been arranged just right. But from a broader perspective, it is simply one outcome among many. Still, this idea raises its own quiet questions. Because if there are many universes, each with different properties, can we ever observe them? Can we test their existence? Can we move beyond imagination into evidence? At present, the answer is uncertain. Some versions of the multiverse idea emerge naturally from existing theories in physics. In certain models of cosmic expansion, for example, different regions of space may evolve independently, leading to separate pocket universes with different conditions. In other approaches, the underlying mathematical structure of reality allows for many consistent solutions, each corresponding to a different universe. And in yet another perspective drawn from quantum theory, every possible outcome of an event may exist in its own branch of reality. These ideas are still being explored. They're not confirmed in the same way that we confirm the motion of planets or the behaviour of atoms. But they offer a way to think about the fine-tuning problem without requiring that our universe be uniquely special. Instead of asking why this universe has the right conditions, we might consider that there are many universes, each with different conditions, and we happen to be in one where those conditions allow us to exist. It is a shift from necessity to possibility, from uniqueness to diversity. And as you rest here, letting this idea unfold gently, you might notice how it changes the feeling of the question. The universe no longer needs to be perfectly arranged. It only needs to be one of the many arrangements where complexity can arise. And yet, even within this framework, something remains quietly remarkable. Because even if there are countless universes, each with its own set of values, the one you experience is still this one, this particular arrangement, this particular balance, the particular unfolding of events, and within it, everything we have explored continues to hold. Atoms remain stable, stars shine, space expands at just the right rate, and life emerges, at least in some places. So while the multiverse idea may soften the sense of uniqueness, it does not remove the sense of wonder. If anything, it expands it. Because instead of a single, finely balanced universe, you're now considering a vast landscape of possibilities where only a few regions allow something like this moment to exist, and that moment is where you are. Not in the silent universes, not in the empty ones, but here, in a universe where the chain of conditions has aligned, where the balance holds, and where awareness has emerged. And as your thoughts begin to slow, drifting gently across these possibilities, the idea settles into something quieter, that whether there is one universe or many, whether this arrangement is unique or one of countless variations, you find yourself in a place where it works, where the rules, the numbers, the timing all allow this experience, this breath, this thought, and perhaps for now, that is enough. As the idea of many possible universes slowly drifts into the background, another possibility begins to take shape. One that feels at first a little different. Not about many universes, but about the nature of this one. Because if the universe depends on rules, and those rules depend on numbers, and those numbers seem to be set in a particular way, it is natural to wonder whether what we are experiencing is not just a physical system, but something more abstract, something structured, something informational. You might begin with a simple observation. Everything we have described, particles, forces, interactions, can be written down. Not perfectly, not completely, but with surprising precision. Equations can describe how objects move, how light behaves, how energy flows. These equations do not exist physically in the universe in the way that stars or atoms do, and yet they capture the behaviour of the universe in a way that is remarkably consistent. It is as though reality follows a kind of code, not code in the sense of a computer program that we can see or touch, but a deeper structure, a set of patterns that can be expressed in mathematical form. And from this observation, some thinkers have wondered, what if the universe is, in some sense, like a simulation? Not necessarily a simulation created by beings in the way we imagine, but a system where the underlying structure is informational, where what we experience as matter and energy emerges from something more fundamental. In this view, the constants we have been exploring, the numbers that shape reality, begin to resemble parameters, settings, values that define how the system behaves. Much like the settings in a simulation determine how objects interact, how forces operate, how environments evolve. If those settings were different, the behavior of the system would change. The same way that adjusting the parameters of a simulation can produce very different outcomes. In some configurations, stable structures emerge, in others they do not, and so the idea of fine-tuning takes on a slightly different tone. Instead of asking why the constants have the values they do, we might imagine that they are simply the values that define this particular instance of reality. Not uniquely necessary, not the only possibility, but one configuration among many. Still, this idea comes with its own quiet challenges, because while it can be tempting to imagine the universe as a kind of simulation, we must also ask what that would mean. If reality is like a simulation, where does the simulation exist? What is it running on? What defines the rules that govern the simulation itself? And can such a system ever be observed from within? At present, these questions remain open. There is no clear way to test whether the universe is a simulation. No experiment that can definitively confirm or deny it. It remains a possibility. A way of thinking about the structure of reality, but not a conclusion, and in that sense it shares something with the multiverse idea we explored earlier. Both offer ways to understand fine-tuning without requiring a single fixed explanation. Both expand the range of possibilities, but neither provides a final answer, and perhaps that is part of the quiet beauty of this exploration. Because each idea, whether it is the delicate balance of physical constants, the perspective of the anthropic principle, the vast landscape of possible universes, or the suggestion of an underlying informational structure, adds a layer to our understanding. But none of them close the question. Instead, they leave space. Space for reflection, space for wonder, and space for the realization that even as our knowledge grows, there are still aspects of reality that remain just beyond our reach. And so, as your thoughts begin to settle, we return to something simple, the distinction between how and why. Science, in its quiet and careful way, has revealed a great deal about how the universe works, how particles interact, how atoms form, how stars shine, how the universe expands. These are questions we can explore, test, and understand with increasing clarity. But when we ask why the universe has these particular rules, why the constants take these specific values, why the balance falls within the narrow range that allows complexity, the answer becomes softer, less defined, not absent but incomplete. And perhaps that is not a failure. Perhaps it is simply where we are, a point in an ongoing exploration, a moment in which we can see far enough to recognize the patterns, but not yet far enough to understand their origin. And as you rest here, letting these ideas drift gently through your mind, there is something quietly comforting in that the universe does not need to be fully understood to be meaningful, that mystery is not something to be removed, but something to be experienced. And within that mystery there is this moment, this quiet awareness, this gentle unfolding of thought, a small reflection of a much larger system, a system that somehow has become capable of noticing itself. And so, we arrive not at a conclusion, but at a place of rest, a place where the question remains, but no longer presses for an answer. Why this universe? Why these rules? Why these numbers? For now, there is no need to resolve it, only to notice that, whatever the deeper explanation may be, You are here, in a universe that works, not necessarily designed, not necessarily unique, but possible. And as the edges of these thoughts begin to soften and your attention drifts gently toward rest, there is one final reflection to carry with you, that in a cosmos shaped by quiet numbers and invisible rules, the fact that anything can exist at all is, in its own way, something to wonder about. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it's just you and the soft hush of rest. Sleep peacefully, wherever and whenever you may be.